Previously, I stated the voltage created by a single point charge, and now I should prove it for you. We'll discuss the concepts of work, potential energy, and potential, aka voltage. Given a point charge, you might think of this as the source of voltage or electric field, as we have previously. Given that point charge capital Q, we're going to use the concept of a test charge again, say lowercase q naught, sitting here in some initial position, and we're going to take it on a journey to a final location here. And ask things like, what force is it feeling? How much work does that force do? And how does it change the potential energy of the test charge and the system as a whole? We'll set this as our coordinate origin r equal to 0 and define a radial unit vector r hat. So this will be a position r equal to, say, RA, and final position will be located at RB. At any moment, the distance between our source charge, capital Q, and the test charge, Q naught, will be variable lowercase r. We know the electric field created by this source charge, and that's kq over r squared, pointing in the r hat direction. This expression is valid for either a positive q, which would point in the plus r hat direction, or a negative q, which would cause the vector E field to point in the negative direction. What force is the source charge placing on the test charge? We know that's Q of the test charge times E created by the source charge. That's a vector expression in terms of the magnitude of that force. We can use Coulomb's law with absolute values of these charges. Okay, how much work is done by the force capital Q on Q naught in moving from location A to location B? Work done by the electric force, I'll call it sub E, from location A to location B is the standard work integral you've seen in UP1 of force dot with dl along the path. On this trip, dl is this vector here, and we have to admit at this point, if we write it in the r variable, that there's a little ambiguity. We haven't stated the sign of the source charge. So this E, vector E field that we defined earlier, will point towards the source charge. I'll call that EQ minus if the charge is negative. And of course there would be an electric field pointing this way. We can call it EQ plus if that charge is positive. That will dictate whether this work is positive or negative when we travel from the coordinate RA to RB. We could say here that the work done by the electric force is positive if what needs to be true to have a positive work. You need a force in the same direction as the dl vector, and that will be true if Q, capital Q, the source charge, is positive. In fact, what we do here will be valid for either positive or negative test charges. So all we need to demand is that the product of capital Q times lowercase q is positive, meaning they have the same sign. And then that work would be negative if the product is negative, meaning they have the opposite sign of charge. Well, something nice happens here. If you look at the magnitude FQ on Q and these plus or minus signs out here, all of that information could be folded into one expression, KQ Q naught, which includes their signs over R squared, right? Because that work will be positive if they have the same sign, and that work will be negative if they have the opposite sign. So it all works out. We can drop the absolute value bars and the plus or minus out front. We have constants out front. Integral of 1 over r squared is minus 1 over r. Our limits are a to rb. Evaluate at those limits. And I'm going to rewrite it in a suggestive way that will be useful later. So negative out front, KQQ over RB minus KQQ over RA. Well, what does this start to look like from the previous video? You had to think about the work energy theorem. The work done by the electric force is the negative change in electric potential energy. We saw that. You could write that as negative quantity final potential energy minus initial potential energy. Then you stare at that expression and you stare at this expression and you say, hey, this quantity sitting here, this first term in the parentheses, could be associated with that potential energy in the final state, at final position, and this is associated with that potential energy in the initial state. So this procedure defines the potential energy, capital U, of a pair of point charges. It's just KQ Q naught over R. You must include charge signs. This is a signed scalar, S-I-G-N-E-D, signed scalar. And our reference point for zero potential energy will be when those 2 point charges cannot feel each other, when they're infinitely far apart. Well, we've already defined voltage as potential energy per unit charge. So this procedure essentially derived for us the voltage of a single point charge, capital Q. Again, you must include the charge sign, and we'll set our reference point of voltage again, just like we did with potential energy. Here, when you go far away from the point charge, the voltage should be 0. And I would say be careful that sometimes the work done by the electric force going from A to B, which is the negative delta U, sometimes textbooks will write it as positive initial potential energy minus final potential energy. I don't care for that layout. I would rather keep it as the negative change, final minus initial. Well, that's the potential energy of a pair. of point charges. The logical extension would be to ask, what's the potential energy of a collection of point charges? We should define a concept called the work to assemble charges from infinite initial separation. The work to assemble the charges is done by an external agent. That work to assemble is the opposite of the work that will be done by the electric force during this process, this trip. And the work done by the electric force, of course, is the negative change in potential energy. So it looks like the work done by the external agent is going to be the positive change in potential energy. And if we start off these charges infinitely far away from one another, of course, then the initial potential energy of the system will be zero. And you're forced to conclude then the final potential energy of the configuration is the amount of work that would need to be done by some external agent to assemble those charges. So as an example, let's find the potential energy of 3 point charges. To determine the total potential energy, you're going to separately consider each pair of point charges and think about the potential energy of each pair. So if I take Q1 and Q2 together, they have potential energy K, Q1, Q2 over the distance which separates them, R1, 2. Then I add the potential energy of this pair, K, Q2, Q3 over R2, 3. That's distance separating those two charges. And then I consider the final unique pair of that trio, which is Q1 and Q3, where the distance R13 is here. That's a specific case with 3 point charges, so let's just generalize to any number n point charges. The potential energy of any system will be K, Qi, Qj over Rij, where those index values I and j start out at 1 for the first charge, and they go up to n. And so that we do not double count, we require that I would be less than j in this summation. You see how that general formula works out in the case of 3 up here, right? You get a term which is KQ1 Q2 over R12. You have the Q2 Q3 over R23 and the Q1 Q3 over R13. You do not have a term which would look like Q2 Q1, because that would double count the potential energy that you already counted of this unique pair of point charges. That's what the I less than j achieves for you. Be careful that you think of the potential energy of this system in a different way, a different context than a different question, which could be to ask, what's the voltage at location P in the vicinity of n charges. That should be an expression that shows superposition of voltage from each point charge. Each one creates KQI over RI, and we have to sum up the contributions to the voltage from all n of the point charges. In the example up here, we could ask at, say, location P is here. Then the voltage at that location with respect to 0 at infinity would be KQ1 over distance R1. That's this distance from P to the charge Q1, plus KQ2 over R2, that would be that distance, plus KQ3 over R3. Be careful to distinguish in your mind voltage at a location from the potential energy of a collection of point charges, which does not have anything to do with a specific location. It's just describing the system as a whole. And it does tell you the potential energy of that final configuration. It tells you how much work would be required by an external agent Smith to take charges Q1, Q2, and Q3 from infinitely far away from each other and bring them together into this final configuration.